recording. I'm just going to work through this rather than answering in particular questions. Sound good? So let's discuss here. Why are you whispering? Are you talking about me? Oh, it's the ass. No, we're not going to do that. X squared minus 8x plus 7. Y'all know that factors, right? And the x minus 7, x minus 1. Right? That'll be helpful to graph. You have a calculator. I mean, that's not really too big a deal. But you get 7 and 1 are zeros, and we can also complete the square on that thing. And we're going to get x minus 4 squared. You can kind of do this in your head, right? There should be a 16 at the end of that, but there's a 7, so we need a minus 9. So we get that. Okay? And solving that, just so we have what y is, so or what x is, that means it's what x equals, you add 9, so that's the square root of y plus 9 plus or minus, and you add a 4 in there. Easy enough? Okay. And we got this line. You guys can tell me where they intersect, but we've got this parabola coming down like this. And 3x plus 6? I don't know, I like that. Is that like this? Okay. What are these points here? Help me out. Oh, they're weird? Oh. We're going to call this point AC. And we're going to call this point BD. All right. But what David said sounds correct. 0 point something or other in there. Okay, that's fine. All right. Yeah, I definitely would use X for this, right? Top's always the same. Bottom's always the same. So we're going to rotate around Y equals 1,000, which is up here. We're going to use disk for that because it's perpendicular. Cool. And let me see here, just to draw this out. Our big R, again, is from top to bottom, so that's 1,000 minus that parabola, and little r is that right there. But it's not changing. So we are going to get pi times the integral of 1,000 minus the parabola, which is kind of a pain in the butt to write out. That's big R squared minus 1,000 minus that line squared dx. That's a parenthesis, and we're going to go from A to B. So, okay, and just somewhere on your paper again, we have a test, just write A equals, B equals, and you should take those out a few places. What is A, Dave? Tell me again, David. 0.092. You got anything after that? Like 0.917. Okay, we'll take it. Yeah, so if I get that we don't have to use these numbers because I just write it out, but if you got to use numbers, you got to take them out like 5 or 6 places. Just store them in your calculator, okay? What's B? 10.908. Okay. We came with that first one? If we're going to rotate around x equals negative 1,000, I'm going to use shells because that makes the most sense. All right? So shells is 2 pi, the integral, of x minus negative 1,000 times the top minus the bottom, that's that line, minus the parabola. If you have any questions, just let me know. But that's that from A to B. Okay? C is around x equals 100. We're going to use shells for that too. Okay? So that's going to be 2 pi, the integral from A to B. But now the axis is on the other side. It's on the right-hand side of my shape, so it's 100 minus x. But the height's the same. It's the line minus the parabola. Everybody got 100% so far? Super geniuses. Okay. Then we saw these cross sections, but they're perpendicular to the x-axis, which is what we want. Okay. The next part's y-axis, which is a pain in the butt. But if they're equilateral triangles, everybody knows the equation for the area of an equilateral triangle is root 3 over 4 times the base squared. Okay. So we're going to integrate all those up. And the base is just 3x minus 6 minus x squared plus 6 minus 8x plus 7 dx squared. Easy enough? Really, it'd be super sweet for me if you all just ace this. because I'm grading it. It makes it so much easier. Okay. Okay. Semicircles. It's all about me, kids. Semicircles is going to be pi over 8 times the integral from a to b. It's almost exactly the same thing, right? It just changes the coefficient out front because the shape is a little bit different. Squared dx. Easy peasy? All right. So, trapezoids with a height of half the base in the plane and a second base that's double the base in the plane. What? Let's check that out. So, we have the base in the plane, right? That's the base we're actually seeing. When you look at our shape, which is basically that, okay? The bases are, let's change up colors so this looks a little bit nicer. The bases are this right here, okay? But once you get past a certain point, they're defined by the line instead of the parabola on both sides. Cool? So we're going to need two integrals here. One is going to go from the bottom of this parabola, which is the point, I forget what it was, 4, -9. Is that right? Cool. Up to this point where these intersect over here, which I initially called A, C. And then to this point here, which we called B, D. So we need an integral from -9 to C, and then another integral from C to D. Cool. But we need a formula for the area of these shapes, so let's talk about that. So that blue line is like the bottom of a trapezoid, like that. Okay? It says that's the bottom of a trapezoid, and the height is equal to half of that base. So the height is small, like not small, but half of that line. Okay? But the base out of the plane is double that base, so it's big. Maybe something like that. So this is our trapezoid. Okay? So the bottom is going to call B. I think we wrote this on the board yesterday. The height is half of that. And the top base is double that. So the area of that super amazing trapezoid is 1/2 the height times base 1 plus base 2. Cool. We're going to multiply that by how thick they are. That's going to be a dy. Cool. What's actually volume now? So I'm not there yet. But we're going to multiply by dy. And we're going to integrate them all up. Cool. That reduces all the way down to, everybody can see, maybe 3/4 base squared. It's okay. You get 3b times b. That's 3b squared. And you get a 1/4 out front. All right. So we need to do two integrals, which again is kind of a pain in the butt, but it's 3/4. The first integral runs from -9 to c, and it's that base. And with parabolas, when you solve this out, do you guys see this? Like we're going to do, I'm going to come way up here, 4 plus that square root, right? That's the right-hand side of that parabola. That's this side. Minus 4 minus that square root. That's the left-hand side. So right minus left. What happens to the 4s? Definitely cancel, and the square roots just double. So we just get 2 of those square roots. The same thing happened when we had like y squared. You got double root x, right? So the base initially is just 2 times the square root of y plus 9. You can write it out big if you want to. You can have this minus this and have that as your whole answer. That's fine. I don't care. I'm going to write. You can even simplify it further since we're squaring it. But that's our first base. That's just 4 times y plus 9 in there. That's all that really is. If you had to do this by hand, we could do that part. Okay? But then the next piece, plus, it has to be 3/4 the integral. Now we got to integrate from c to d. So again, we're integrating the shape. Cool. The bottom part was there, right? Parabola minus parabola. Now we got to do the right side of the parabola minus that line. So it is, I forget already, 4 plus root y plus 9. That's the right side. Minus the line, which I didn't solve for y. What was that line? 3x plus 6? Is that what it was? Cool. So x is 1/3 y minus 6, which if you distribute, which I'm going to do, is really a 2 in there, so we don't need these. Okay. So it's minus 1/3 y minus 2. That's the whole base squared dy. Wasn't that fun? Okay, yeah, that was fun. It was good. We had a good time. Okay, the other one's going to look similar. I don't know what shape we're talking about over here. Isosceles right triangles with leg in the plane. That means it looks like this. That's half a square. So it's just 1/2 the integral from -9 to c of 2 square root y plus 9 squared dy plus 1/2 the integral from c to d of 4 plus the square root of y plus 9 minus that line, which was 1/3 y minus 2, I think, squared dy. If I mess up, let me know, gang. I might forget a squared or something. Everybody good on what just happened there? 1 and 2, like for E, were like the same as that question, just that the coefficient out front changes. Easy? Okay. Consider this now. What's wrong with me? We got sine of x and cosecant of x between pi over 6 and pi over 3. All right, I'm going to do that down here. So, this is what I heard y'all say yesterday, like there's no like bounds on this. It doesn't stop. That's what the x values are for, okay? So cosecant looks like this thing coming down, and sine on this interval is coming up like this, and they just stop. So we want the area in there. It's okay? I'm definitely going to use x here, because I don't feel like switching that to y. We'd arc sine and arc cosecant. That'd be weird. Cool. If we want to rotate around the line y equals -15, which is down here. We can use disk method for that. So you can get pi times the integral from, what do we say, pi over 6 to pi over 3? Yo, this is so old, I didn't even know how to put pi's into my document. Look at that. It's embarrassing. Pi over 6 to pi over 3. What is this going to be? The top thing, cosecant plus 15 squared minus sine plus 15 squared. It's okay. Really? We're all 100% kids? Okay. You're all so good at this. That's A. B. When we rotate around x equals 20, we're going to want to use shells because I want to use x. So we're going to say that's 2 pi. Still the integral from pi over 6 to pi over 3. But now we're going around 20. So it's 20. Whoa, what are you doing here? Oh, you dummy. I don't want you here. Ah! Foiled. Yeah, get out. 20 minus x. That was great. 20 minus x, and the height is what? Cosecant minus sine. And C, what are we doing? Volume, squares. So that's pretty easy, right? That's the integral from pi over 6 to pi over 3. That's a 6 of cosecant of x minus sine of x squared dx. Okay, real quick question, pop quiz. What number is that? It's a 7, David, right? David wrote that as a 3 on it. He said that. Sorry, man. To handle these off-length questions, look, I try to cook up some weird things here. All we're doing, you got to pick x or y to solve for. It doesn't matter which one. Okay, it kind of technically matters, but I'm going to solve because if you solve for y, you get a plus or minus going on. Does that make sense? It's kind of weird, but because the y's are positive from like 1 to 4, I mean from 1 to 8. It doesn't matter the negative side, but you should kind of worry about what this looks like. You might want to graph it and see. I'm going to solve for x just because it doesn't have 2 pieces. So x is just y to the 2/3. So, okay? All I need to do is derive that. So we're going to find x prime, which is with respect to y. That's going to be 2 over 3 cubed root y. Is that right? We're going to square that. We're going to add 1. We're going to take the square root. That's arc length. So we're going to integrate the square root of 1 plus 4 over 9 y to the 2/3 dy, and we're going to go from 1 to 8. Okay, you could also just solve for x or solve for y equals in terms of x and do the same exact thing dx, but your integral would go from 1 to 4. Everybody understand what I'm saying to you? Okay, someone asked me the other day too, how do I put integral with y's into the calculator? Talked about this, your calculator is not sentient, it doesn't know what variables you're talking about, it just has a x is like a placeholder. So if you have y's or g's or r's or k's, you just plug that in, okay? You can use x in the calculator, that's fine. All right. Yeah, this arc length, we derive it. So dy dx is 2x minus 1 over 8x. This is one we can do by hand as well, but I'm not going to make you do all this algebra. Everybody good on that? That's a derivative. We're going to square that thing, add 1 to it, and integrate it. So the arc length is the integral from 1 to 2, the square root of 1 plus 2x minus 1 over 8x squared dx. All right. And just for fun, let's just do this out by hand, just for fun, so you guys see what this looks like, okay? The reason why, like, a textbook would give you a question like this in particular, if you square that out, you get 4x squared minus 2 times both of them. You with me here? See how the x's will cancel? Like 2x times 1 over 8x is what? 1 over 4. But we're doubling that because when you square something out, you double the middle term. So 1 over 4 becomes a half, and then you're adding that to 1 over 64x squared. Is that okay? Now we're adding 1 plus that. That's all the square root. So we got to get a common denominator. The common denominator is going to be 64x squared. Okay? Okay, that means the 1 is going to become, I'm going to write it down here, 64x squared. It's all over. The plus 4x squared is going to become, everybody now, 256 x to the 4th. The 1/2 is going to become 32x squared. And the 64x squared is going to become just a 1 there, right? Now remember, those are, did I mess up? Does this look good? These are all in a big square root, right? Which means it's technically the square root of the top and the square root of the bottom. The only way we're going to be able to handle this integral is if those square roots go away. That's why this particular example is chosen in a textbook. Do you see the bottom is just 8x? It's technically the absolute value of x. I'm talking about that. But x is going from 1 to 2, so it's positive, so it doesn't matter. Okay? But that means the numerator, again, thinking what the authors are thinking, has to be a perfect square. If you put that all together, look at this craziness. We're going to get 256x to the 4th, which seems a little daunting, perhaps, plus 32x plus 1. Yeah? X squared. Over 8x. And we're still integrating this. I'm going to simplify the whole stupid thing now. Anybody know how that factors? What is that? It's a perfect square. How would I get this out of a perfect square, folks? 16x squared. Yeah? How would I get this out of a perfect square? 1. So that's only 16x squared plus 1 if the middle term is 16x squared times 1 times 2. And it happens to be 32x squared. So that whole numerator becomes, it's in a square root still, remember? Just the numerator is now. But that just becomes 16x squared plus 1. It's squared in a square root, so it cancels out. And that's over 8x. So that whole integral boils all the way down to 2x plus 1/8 x to the negative 1 dx. So we can actually do it. That's why they pick an example like that. I'm not going to make you do this by hand. I just want to show you the math one time to see what happens there. It's okay? So, all right, great. You can integrate that by hand and plug in and get an answer or whatever. We'll do it on a calculator. All right. And there's the last one. Oh, derive the area formula for surface area. Did you guys do that? You're like little walking textbooks, like calculus machines. Yeah, when I ask you to find something using the trapezoid rule, disregard like the trapezoid rule until you get your integral. And then once you get your integral, you're going to use the trapezoid rule as if that was the integral you were given to begin with. Okay, what's the trapezoid rule is not a good question right now, David. Okay. So we want the arc length of this. We'll write it out. Okay, so y equals 1 over x. The derivative of that is negative 1 over x squared. I have terrible news. We might not have time for our bullet quiz. Is negative 1 over x squared. Yes? If we square that and add 1 to it and integrate it, the integral we want to handle is 1 plus 1 over x to the 4th dx. True? From 1 to 2. Yes. This has nothing to do with the trapezoid yet. The trapezoid rule. Okay? That's the integral that tells me the length of that curve. Cool? We can put that into a calculator and it will just tell us the answer. That'd be super nice. Or I could ask you to do the trapezoid rule with 4 subintervals. Okay? Which is what I did. So remember what trapezoid rule says. I don't know what the graph of that looks like, but let's say it looks like this. From 1 to 2. Right? Our goal, our quest, if you will, is to find the area under that curve. What we're going to do is chop it into 4 sections because the math gods had chosen 4. Okay, that's not up to us to choose. It says 4, and we're going to put a trapezoid in there. Every single one of these becomes a trapezoid. Did Druva just fall asleep? Is that what just happened? This is like an ASMR. Look at that. Good. Anyway, you don't need to remember a fancy rule. What you're going to do is put into your calculator y1 is the square root of 1 plus 1 over x to the 4th. And then you're going to type out the area of each trapezoid, which is 1/2 the height, which is 0.25, f of 1 plus f of 1.25. Can you handle that? That's the first trapezoid. Plus 1/2 times 0.25. Isn't this fun? F of 1.25 plus f of 1.5. We can write this shorthand if you remember the actual trapezoid formula. Like you factor all this junk out. That's in the textbook. It doesn't work all the time if the intervals aren't the same length. Remember, we should have 4 of these trapezoids, right? 1/2 times 0.25. F of 1.5 plus f of 1.75. And sadly, the adventure comes to an end with the last trapezoid here. F of 1.75 plus f of 2. There you go, 4 trapezoids. They will add up to approximately the area under that curve, which was approximately equal to the length of the original curve. Make sense? So we did like a transformation here. We wonder the length of the curve. We transfer that into a question about the area of this function, right? And we transfer that into a geometric question and just find the area of a bunch of trapezoids under the curve. Cool. I might know what that answer is. I might do this. I had it on the old answer key and I deleted it. Wasn't good. Okay. 0.697. We are going to take Sam's word for that. Let us know in the comments if Sam is right. Remember to like and subscribe. Yeah. All right.